Welcome back. It's my pleasure to introduce the next speaker, Dina Katabi. She's a Thuan and Nicole Pham Professor, MacArthur Fellow, directs the MIT Center for Wireless Networks and Mobile Computing in the MIT Computer Science and Artificial Intelligence Lab. Dina, thank you.
Hi, everyone. It's a pleasure to be here. I'm a computer scientist, so being and interacting with this audience is very exciting for me. My area is AI and digital health. And my interest, particularly my recent interest, is how we can use AI to understand the brain, its diseases, and its therapies. So why? Why should we try to use AI to understand the brain in the first place? And the answer is simple, because we really don't have that many tools for understanding and measuring the brain. Okay? So if you think about how you measure the brain, I mean, it's not like we have really good success with blood tests or anything that is easy to obtain. So if AI can yield information and measurement, concrete measurement about the state of our brain, particularly in human, where we know that at least in neuroscience, it's much harder to translate from animals to humans. If we can use AI for that, that would be very useful. But then the second question is how? How can we use AI to measure the human brain without putting electrodes in people's brain and asking them to live like that so that we can keep collecting measurements? So we have developed a simple way in my lab, which is basically, it's based on something that looks very much like your Wi-Fi box at home. So think about if you have something that a radio device that looks like your Wi-Fi box that sits in the background of the home and analyze these radio waves as they bounce off people and objects in the environment. So analyze this electromagnetic field, and from that, being able to get people motor symptoms, like for diseases like Parkinson, Huntington, et cetera. Be able to get their sleep state, not only getting when they sleep versus when they are awake, but knowing, for example, whether they are in slow wave, for example, N3, et cetera, or not. Being able to get their respiration signal, and if they have apnea, for example, detecting it, and if there are diseases that involve interaction with a caregiver, being able to also monitor that. And all passively, without asking people to wear sensors or to write PROs or to report anything. Now, that might seem like La La Land. I see people, what is this? But actually, it's not. It's a real device that is used today with actual patients. So it's all enabled by this revolution in neural networks and AI that allows us to analyze something that we as a human may not even understand very well, such as electromagnetic fields. And we call this device the Emerald device. And I'm going to show you throughout this talk how it enables us to understand diseases, brain diseases, and actually even others. So let's start. I'm going to start very early on with some of our earlier experiments in the computer science lab here across the street. So this is one of our offices in CSAIL. Our device is not even in the same room. We are in the adjacent office behind the wall. And we're going to monitor this person as he moves around just by analyzing how his movement is changing the electromagnetic waves around him. Okay? This red dot here is where the device thinks that he's standing right now. So think of it for diseases that involve motor symptoms that you want to understand the movement in the home. So let me play this and see as he moves how the red dot is tracking him. And remember, he doesn't have any wearables, any cell phone or Apple Watch or anything. It's really just based on how, when he moves, it changes the electromagnetic waves. So it tracks him pretty accurately. So of course, everything that we do, we compare to the gold standard. In the case of tracking motion, the gold standard is related to something called the Viken motion capture room. So it's a room where the whole ceiling is planted with infrared cameras, and there are infrared markers that you put on people. You see these kind of systems in rehabilitation hospitals, like the Spalding Hospital here nearby. And we show that it is highly accurate. The other thing is that, of course, I showed you one person, but we can track when even there are multiple people in the environment. Now, I started by saying this is our earlier result. This is when we started. So let me show you what we can do today. So now, the big frame is what the wireless device infers through the wall. That small window at the top is like what is happening inside the room. And I'm just showing you what's happening so that you can compare what we get with wireless signal through a wall and versus what's happening inside a room. So let's play this video. So now you see that when he sits, you are seeing a full skeleton. It's not a dot. You know that he's sitting as opposed to just his location. He stands up. When he moves with his right foot, you see the right foot. When he moves with the left foot, you see the left foot. All through a wall, based on how our bodies change the electromagnetic waves around us with multiple people in the environment. So these electromagnetic waves that we all like swim in have so much power. And if we can interpret that power, we can learn so much about physiological signals. I showed you something that is related to motor symptoms so far, but what else can we monitor? So when you go to sleep, your brain waves change, and you enter different stages: awake, light sleep, deep sleep, REM, rapid eye movement. And these sleep stages, of course, are related to our different sleep disorders, like insomnia, etc. But in the case of at least neurological diseases, sleep is a platform for almost everything. In fact, not just neurological diseases. Almost any disease that I've interacted with patient in that disease or talked to the doctor, sleep is a platform for the vast majority of diseases. Okay, so how can we understand these sleep stages? If we can understand them, for example, there are results that relate to slow waves during deep sleep to Alzheimer's. There are results about depression. When we know in depression, for example, one of the signs of depression, REM, start happening early in sleep. And in fact, we know also antidepressants tend to increase REM latency. So if we can understand these sleep stages very well, we can understand mood disorder, we can understand neurological neurodegeneration. How can we get that? Today, if you want sleep stages accurately, you have to send someone to a sleep lab. They put these electrodes on his head and body. And yeah, he's not happy. This is actually MGH lab. But more important than whether he's happy or not, actually, how is it possible to even imagine that this would be normal sleep? And not only that, of course, we know even if that sleep or that capture was normal for that night, not every night is the same. Maybe today he is more tired, or he had a big fight and there is so much on his brain. So how can we measure these in the person's home? Let me show you what we do. So this is actually our device. Transmit very low power wireless signal, analyzes the reflection using AI, and spits out the hypnogram. So the hypnogram is exactly what you get in a sleep lab. So for every 30 seconds of sleep, it tells you this is light sleep, this is deep sleep, this is REM. So it tells you how your brain is moving between these different sleep stages, leaving one, entering to the next, and so on. So that is a hypnogram. That's exactly what we get in his own bedroom every single night you are getting a sleep study. And of course, as I said, everything that we do, we compare to the gold standard and have peer-reviewed publication. And the gold standard in the case of sleep is PSG, is that stuff with all of the electrodes that I showed you. So this guy is sitting and reading. What you see on the screen is nothing but his inhales, exhales, inhales, exhales. We ask him to hold his breath. You see the signal stays at a steady level because he inhaled, he did not exhale. So we can also track your respiratory signal. And again, everything is compared to the gold standard. In the case of breathing, is an FDA-approved chest belt. So over the last 3 years, so we have been developing this technology for many years, but over the last 3 years, we have been actually out there, this technology being used with real patients to monitor their diseases. So what I showed you so far is the tech, what we can measure. But what I'm going to show you in the next 10, 15 minutes is what information we can get about diseases once we measure them with this technology. Okay? And as I said, we are in many diseases. We started in Parkinson. We work with people who have depression, Alzheimer's. So I'm going to talk about neurological diseases, but also we are in autoimmune diseases, Crohn, lupus, RA, rare diseases, Rett syndrome, FSHD, atopic dermatitis for kids and adults as well. So a variety of diseases. So as we are talking now, these devices sitting in patients' homes collecting data in all of these diseases. Okay, let's talk about, so I'm going to take examples in neurodegeneration and in mood disorder. So let's start with neurodegeneration. Let's start with Parkinson's disease. So I'm going to talk about results from 2 studies. One is in Nature Medicine, and the other one is in Science Translational Medicine. So let's start talking about Parkinson's disease. So Parkinson, of course, is a neurodegenerative disease. I mean, many people do not know that Parkinson is the fastest growing neurological disease in the world. So it is the steepest growing. It is the second most common neurological disease after Alzheimer's. So like for Parkinson, one of the biggest problems, and also actually for Alzheimer's, the vast majority of neurodegenerative diseases, is late detection of the disease. So the disease starts in the brain, and we believe that, well, not me, I'm a computer scientist, but the medical community believes that the disease typically starts about 5 to 10, sometimes even like 15 years before the actual diagnosis of the disease. And actually, the fact that the diagnosis comes very late is very detrimental, because by the time people get a diagnosis, typically what happens is that the dopaminergic neurons in the brain, 50 to 80% of them are already impaired. So these dopaminergic neurons are the neurons underlying, like their impairment is what is related to Parkinson's disease. So if the neurons are already 80% impaired by the time of diagnosis, what is the chance that we are going to be able to treat the disease? And in fact, today we don't have a way to treat the disease. All that we have are drugs that can contain the symptoms or address the symptoms. So one of the biggest things is, how do we diagnose or detect Parkinson's early? And one of the key reasons why we detect Parkinson's late is that we have to, today we rely on the appearance of the motor symptoms. So Parkinson, you have the tremor. In Parkinson, you have stiffness of motion. And typically, we have to see these symptoms to be able to diagnose the disease. But these symptoms happen later in the disease. So if we have any chance of detecting the disease early, we really need to detect it from something other than motor symptoms. Okay? What do you think? What can we use to detect Parkinson's? So we are computer scientists. We went, me and my students, and we looked at the literature. It was very interesting. You read the literature, and even as early as the writing of James Parkinson, the doctor after whom we call the disease, even in his own writing, you see that he talks about breathing of patients changing. Okay? Well, of course, so I went and I work with a lovely collaborator, of course, an expert, Ray Dorsey, an expert on Parkinson's. And I said, why don't people try to use breathing, for example, to detect Parkinson's disease? And he was like, I mean, yeah, we know breathing changes, but nobody knows how to detect it from breathing. And I said, what, can we try? Do you think if AI maybe find a signal? And Ray is a very easygoing guy. It's like, Okay, try. And what do you guys think? Let me show you. So basically, the question that we started with, can AI detect Parkinson's from nocturnal breathing? So we took many nights of breathing signal. We trained a neural network to answer 2 questions. Does this person have Parkinson's disease? And if they do have Parkinson's disease, what is the severity of their disease according to the gold standard, which is something called the MDS-UPDRS? OK, and this is a large study that we pulled so much data. We pulled data from our studies with the wireless signal, as well as sleep studies that were done with a large number of participants at MGH, Mayo Clinic, and University of Rochester Medical Center. So we have about 7,000 individuals. 700 of them have Parkinson's disease. And let me show you the results. And this is actually the result that we published in Nature Medicine. So here is the result. So if you haven't seen these graphs before, I mean, you really don't need to worry about the graphs so much. I mean, these are called rock graphs. On the one axis, you see sensitivity. On the other one is actually 1 minus specificity. But the only thing that you have to worry about is this number, the AUC, the area under the curve. You can interpret it as accuracy. So with accuracy about 90%, we can take a night of respiration, nocturnal breathing from someone, and with accuracy 90%, we can tell this person has Parkinson's or no, this person doesn't have Parkinson's. Now, this was very surprising and very interesting. And as I said, this is with very large data set, so we know that the signal is strong and does exist. Of course, we want to do more studies to even establish it further. But the next question that we try to answer is how early can we detect the disease? Or can we detect the disease before the diagnosis of the patient? And here, actually, of course, it's harder because we need to measure the patients that are going to eventually develop Parkinson. And it's kind of like chicken and egg problem. But we discovered that there is one study that we have access to that where the breathing signal of people was collected in 2 visits that are separated by 6 years. So there are people who came on the first visit and said, I don't have Parkinson's. But then later, 6 years later, on the second visit, they came and they said, I got diagnosed with Parkinson sometime along this time axis. So what we did is to go and take their data from the first visit and say, OK, can we tell with the machine learning that those people are going to develop Parkinson's later? So here are the results. So this study has about 500 individuals. In red, you see the people who, in the first visit, they didn't have Parkinson's. 6 years later, they also said, I was not diagnosed with Parkinson's. In blue, you see the people that in the first visit did not have Parkinson's, but 6 years later, they came and said, I got diagnosed with Parkinson's. And it's pretty clear that the machine learning can tell that these are very different. In fact, 75% of the people who eventually develop Parkinson, the machine learning model is already saying, I think they have Parkinson. These don't look normal to me. So of course, this is like the first study, and we have we really need much larger study and with more people to establish these results further. But it is good step that telling us that really there is something that this machine learning model able to detect from breathing, and that whatever those features are, there is enough evidence to believe that they happen early on and can help in early detection. OK. Another thing that is very interesting is progression. So one of the big problems if you are developing a drug for Alzheimer's or Parkinson's or any neurodegenerative disease is there are slow diseases, particularly like in Parkinson, it's a really slow disease. So when you develop a drug and you want to say, OK, the people who I give this therapy to are going to, it's going to help them, you have to wait for a long time to compare them with other people who are not taking your therapy. So there is a huge need for something called progression marker of the disease. So we looked at in our data whether actually we can see also a progression marker. So I showed you earlier like a detection or diagnostic marker. So now let's look at the progression marker. So let me just show you illustrative results from 2 individuals first so that we understand what we are looking at here. So here, this is a control person, a healthy individual, and this is somebody who has Parkinson, and they are the same age. They are age match. And what you see on the x-axis is time. So this is 1 year, so 0 to 12 months for both individuals. On the y-axis, you see their gait speed, like how fast they walk, right? And you see how this walking speed is changing over 1 year period, right? Now, you see, I mean, interestingly, of course, that the person who is healthy, although he is as old as this person, but he's starting with higher walking speed. That's expected. I mean, if you have Parkinson, you're going to be slower. But the thing that is even more interesting and more related to progression marker is the slope of the change. So this guy, his speed is degrading twice as much as someone who's healthy. Now, again, remember, these are old people. So all of us, when we are in our 80s and late 80s, early 90s, we are going to slow down. Every year that passes, we slow down. So it's not surprising that the control is slowing down over a 1 year period. But if you have Parkinson's, you're going to slow down on average twice as much as someone your age, but who doesn't have Parkinson. And this is, of course, just 2 people, but let's look at the cohort. So the cohort of the healthy individual is in blue, or the control in blue. The red one are the Parkinson cohort, and this is a linear mixed effect model, and as you can see, it shows exactly the same thing. So people, the cohort with Parkinson's disease are slowing down almost twice as much as the healthy control. And this is actually the first time anyone was able to show statistically significant progression that will separate these 2 groups over just 1 year period. Now, 1 year might look like, okay, it's a long time, but if you have, I'm going to show you how many patients you will need if you want to show statistical significance over just 1 year with other markers of the disease. So what does that mean? What does that mean if you are developing a drug or therapy for Parkinson's disease? If you are developing a drug or therapy, you need to apply that therapy to some arm and have another arm that doesn't take the therapy and compare them to show that you have statistical significance. The problem is how many people you need in your clinical trials so that you can have what we call statistical significance, that these results are really statistically sound, are not just random guesses. And if you are monitoring people only for 1 year and you use standard metrics such as, I told you the MDS-UPDRS is the standard way we measure Parkinson, then if we put on the x-axis the efficacy of your therapy, so if you have a 30% efficacy in Parkinson's, you are golden. And that would be amazing because we don't have any therapy for Parkinson today. Okay? But look at how big your clinical trial has to be, like 11,000 individuals, to show that this therapy is actually statistically significant. But here's how many people you need in your clinical trial if you are using this new marker. And that, of course, is very important. This is if you want the trial, if you want to monitor someone only for 1 year. So what people do is they monitor. Of course, they cannot run 11,000 individual in one trial. So what Parkinson particularly, because that's hard to find that many people. So what they do is smaller trials over a longer time, and in many cases, so far we have no drug or no therapy for Parkinson, so they don't show statistical significance. Let's talk about depression. So today, how do you assess, when you give someone antidepressant? Right? How do you assess whether it's working for them or not? You just ask them. Right? Is that working for you? How do you feel? How did you feel before? How do you feel now? If they are saying that it's not working, they're feeling bad, you say, oh, let's wait a bit to see whether things are going to improve. And then you wait a bit, you are not sure to wait longer or not. So we really have no way of actually measuring something concrete about whether the antidepressant is working or not. Can we do that with AI? So we did something very motivated with our Parkinson study. We did something very similar. So we took the wireless signal, and from wireless signal, we know that we can move to breathing. So we moved from wireless signal to breathing, and then we fed the nocturnal breathing during sleep to a neural network. We trained this neural network to answer the following question. Is this person taking antidepressant or not? The intent is not to know whether they are taking antidepressant or not. I mean, that is known unless they are not compliant. But the intent, if the machine learning can answer this question just from their breathing taken from the wireless signal, then something has changed about their physiology that is related to the antidepressant that the machine learning is able to see. Okay? So let's see the result. These are very similar to the previous curve. So the ROC curve on one axis, sensitivity, specificity. Again, the important number is this, with accuracy 86%. The machine learning knows just from one night of nocturnal breathing whether this person is taking antidepressant or not. And actually, we tried it on a variety of different antidepressants, whether it is SSRI or SNRI or other that even like other mechanisms. So far, it is working beautifully across different types of drugs. I just want to show you an example of what is happening here. So here you see time, x-axis. This is an example of person who started Prozac. So in the middle of the study, he was put on Prozac. What you see, time on the x-axis, and this output of the machine learning on the y-axis. And the orange line is just a smoothing of the output. And you can see, like at the beginning of the study, the machine learning is saying, no, he's not on antidepressants. This person is not on antidepressant. And then when he started actually taking the antidepressant, something very interesting happens. First, I mean, you see a big jump immediately. Okay? So he moved from not taking antidepressant to I think that he's taking antidepressant. But as the jump continued to increase gradually over time, which is very interesting. That's what we know about antidepressant. It's not like their effect gradually improve and takes time. So what is really interesting that it's seeing the effect, is seeing some initial effect very quickly, but also that effect is consolidating over time. And the machine learning in its monitoring is able to see the effect of consolidation and becoming stronger and more certain that this person is on antidepressant. I want to end with generative AI. I'm sure all of you guys have heard of ChatGPT, and the vast majority of you, if not all of you, are using it. So that is generative AI. That is like being able to generate interesting modality from some prompt that we give to the model. And I'm going to show you how we can use these ideas I'm going to use Alzheimer's as an example. OK, so the question that we asked in my group, can we use generative AI for brain data? What do I mean by that? So today, you have models. Actually, this is like a model called DALL-E. So in ChatGPT, you use a prompt that is text, it generates text. In this model, you use a prompt that is text, it generates an image. So you can tell the model, OK, generate for me a dog that is playing trumpet. It will generate an image of a dog playing trumpet. Okay? So what we want is something like that. I want to put in, as a prompt, I want to put breathing from my wireless signal completely passively collected. And I want to say, generate for me brain data, like EEG, for example. Why do I believe that this is at all even feasible? Let me just try to explain. So if you think about this, what is happening here? What is happening is that the model is understand consistency, understand like this is a caption of this image. There has to be in this image what is in this prompt. These components that are in the prompt has to appear in the image. So the generative model has somehow, by looking at so much data, understood what are the components, what are the concepts in speech, what are the concepts in images, and how to link them together. So this is exactly what I want to do here. I want the generative model to understand what are the concepts that are associated with changes in the respiratory signal, that are associated with different diseases, different mental states, and have that model use them to generate the concept in EEG. You can, in some sense, you can think actually about our physiological signals as they are language, in the sense that they are not random. We know that our physiological signals have like building blocks. You can think of these as words. And these don't appear randomly. There is some underlying grammar and semantics that control them. It's just we don't understand that. But we don't need to understand it for AI to understand it. I can train a model to generate Chinese. I don't speak Chinese. I don't understand Chinese. That's not an issue. So this is what we wanted. Let me show you. This is very recent result. So this is the EEG spectrogram of an individual who has Alzheimer's disease. He's 83 years old. This is the actual EEG signal. This is what our model has generated for this person. As you can see, I mean, visually, it looks very similar. Right? But then one of the things that, OK, we can look at it visually, but then the next question that we can ask, how much medical information this EEG actually captures? I mean, like if it looks visually, that's good. But the next question that I want to ask is, what if the generated EEG can detect Alzheimer's better than the ground truth EEG? Okay? Because how do I test that generated EEG? Because I can look at it, maybe it looks the same, but maybe it's like, I don't know, like in images, like if you are missing the ear of the cat, you can tell. Or the tail or the nose, you can tell this is not a right cat. But maybe like it's missing the ear of the EEG, but it's not. We are not visually. We don't know what should be in EEG of an Alzheimer's patient. So what is best is to go and use these generated EEG and ask the question: can you detect Alzheimer's in the generated EEG the same way or better or worse than you could detect it from the original EEG? So detecting Alzheimer's from an EEG is on its own not an easy task. So we trained with both the ground truth EEG and the generated EEG. And let me show you the results. So here on the x-axis is we see like these two things. This is the accuracy on the y-axis, and this is by training with the ground truth EEG, with the actual EEG spectrogram of the individual. And these are just generated EEG generated from their breathing signal. And the different circles are different runs. And you can see that actually it's more accurate than the ground truth EEG. Now this is very, of course, surprising result. How can you be more accurate than the ground truth? I'm happy to, we have hypotheses why this might be true, and I'm happy to share if people are interested in that question. But to finish, this is my last slide. So really what we are doing now, we are really interested in starting this foundational AI for brain research. How we can because basically going back to what I was just telling you a few minutes ago, is that our physiological signals are a language that has its own grammar, has its own meaning, semantics, information. Like when you see someone's EEG or respiratory signal, they are not random. They have building blocks. They have a grammar that mean how they progress over time based on our diseases, gender, mental health, all of that stuff. And AI can now think about a foundational model that instead of understanding natural languages like what ChatGPT does, tries to understand this physiological language and try through that to understand the brain. That's, of course, our hope and dream, and the thing that we intend to spend the next few years looking into very actively. Thank you very much.
So we have about 10 minutes for questions. Is this? There's one back here.
Thank you. A question about what you just presented. I might have missed something, but does it follow that breathing predicts Alzheimer's if that EEG is somewhat?
So the EEG is generated based on the breathing of the individual. So the first thing is we can, from breathing, generate pretty accurate EEG. I can't say that it is not missing information. Of course, it's missing information, but it is capturing, it seems, the bigger structures that you see in an EEG spectrogram, which is what the spectrogram images of EEG that I showed you. That we know now for sure because of our models. Now, yeah, then we use these EEG generated from breathing and we trained a second machine learning model to detect Alzheimer's, and it has the accuracy that you saw, over 80% accuracy, and that, yeah, based on the EEG that was generated from breathing.
Right. Okay. One more quick question. Have you ever applied your device for patients with epilepsy for seizure detection?
Yeah. So we actually did work on, we have ongoing work with Brigham and women to look at individuals with epilepsy. We can detect epilepsy. I mean, detecting like tonic-clonic epilepsy, of course, is easier because just direct because we measure the motion. We are interested also to understand, even when there is no seizure, can you actually differentiate what happens? Like, can you actually identify individuals who have epilepsy outside the seizure time, even, like, because most likely what is happening is not just happening during seizure time, it's just we see it manifests during seizure time. So we are trying to look at those issues, but of course, like everything in medicine, really we have to monitor enough patients to be able to run our AI models.
Great, thank you.
I was curious about your antidepressant finding. Can you get feature importance from those models? Are there particular features that you can identify that predict whether someone's on an antidepressant?
Yeah. So there are multiple things that are here that are, the Parkinson is all published. I mean, the Alzheimer and the antidepressant stuff, we are like preparing for the publication. But so yeah, there are features that we can see. So just to give you like an idea, so if you look at the literature about antidepressant, but it is very easy to find evidence that when people take antidepressant, the REM latency increases. So people tells you that basically REM tends to happen early on during sleep in people who have depression, and when people take antidepressant, actually the REM latency increases. This is what people think in general because they see one night of sleep. Okay? When you see one night of sleep, what happens is REM appeared later overall in people who take antidepressant. So you say, oh, REM latency has increased. But actually, what happens really is that antidepressant knock off the REM in the first cycle of sleep. So the reason why people say REM latency increases is because they are not seeing the REM during the first cycle, they are seeing the REM during the second cycle of sleep, and of course that takes longer time. But it's really not just like the cycle, just it took longer time within the same cycle for REM. We know sleep goes in cycles. It's not like it took longer time for the REM to appear in the first cycle. No, actually it got knocked off from the first cycle. So this is very interesting. So that we know in our data, in our manuscript, we are putting all of these results. And you see it in, as I said, in the variety of like different types of antidepressant. Then the next question to ask, which is a really interesting question, why the first cycle of sleep? What is so different? It's not like people take these antidepressants just before sleeping and it's like, the lifetime of the drug just affect only the first cycle. There is something more fundamental about the homeostasis, I think, about the different neurotransmitters in the first cycle versus the second and the third cycle, and how they interact with the antidepressant. So one of the most interesting thing, I think, is that when we analyze this data from the AI models and the features, as you are saying, is to go back and work with people with a medical doctors and neuroscientists, people who understand pharmacology, to understand the different pathways and basically having the data highlighting different pathways.
Thank you for your impressive talk. I was wondering if you could talk a little bit more about the technology behind the Wi-Fi, the Emerald, and if there's a possibility to scale this, maybe, I don't know, with 4G, 5G, and so on in the future.
Yeah. So basically, it's not your off-the-shelf Wi-Fi box. It's really a smarter Wi-Fi box or a smarter radio device that looks like a Wi-Fi box that we built. And the reason why you need to build something that is not exactly off the shelf, because I mean the communication devices are optimized, of course, for communication. So they are loaded with messages that the messages that you want to say about the communication that is ongoing, which is not optimal for if your message is the environment, basically. So that's so it's not an off-the-shelf Wi-Fi box. But in principle, it's like any electronics. If you build it at scale, it will be the price and the size and everything like a Wi-Fi box. There is no reason that would prevent scaling. It's just that, like any new technology, as you want to scale it first, I mean, we are at MIT, we're not going to build like 100,000 devices unless we want MIT to go bankrupt. Yes.
Is there a possibility to use a device like this? Thank you. So a question I have here is there a possibility to use a device like this or multiple devices like this in a sense, in every person's home as something that can prevent things like Parkinson's from ever occurring? Kind of like so for example, when you have a building, you usually have a smoke alarm and you have a fire extinguisher. Then you go to a big building like this, you also have water that comes from the ceiling. So it's all preventative. So you don't have to even think, hey, could I have Parkinson's to go in and to try to check this out?
So there are two related questions here. One related question, should that be in every home, at least every home, if a person that has a patient of some sort or like somebody who has high risk? And the answer is yes, that's feasible in the future. In fact, that's our vision that at some point that will be like a smoke detector. So it's like health problem detector. But there is a second thing, which is in your question, which is, can we prevent these diseases before they occur? And again, I'm not a medical doctor, although I was supposed to be a medical doctor. I come from a family with all medical doctors. I went to 1 year of medicine. In my country, there is no pre-med, so you go directly to medicine. And if you are a topper in like the national exam, the med school is the highest rank, so you go to medicine. And I went to 1 year of medicine and did well. Actually, was the topper of that batch. And then it's like I was a teenager and said, oh no, I cannot like live without math. But so that is also a disease that teenager thinking that maybe can help. But going back to what you were saying, so one of the essential things is there is a lot of now evidence, and also you can take it as a hypothesis. Many people believe that our immune system and understanding the immune system, how it interacts with the diseases and the inflammation, is very much the way to be able to treat diseases, understand them, and prevent them. One of the really interesting things about the immune system is a dynamic system. And when I talk about immune, I also am talking in the brain, of course, the microglia system that clean the brain from toxins that might accumulate. And in Parkinson, the toxins are alpha-synuclein. In Alzheimer's, the toxins are beta amyloid. And in ALS, there are Lewy bodies. But there is this immune system that is cleaning the brain. And one hypothesis is that it's a deficiency in cleaning from those toxins that lead to eventually the garbage accumulating, causing Parkinson, Alzheimer, etc. And each one of us is slightly different have different garbage in their brain than the other person, that if that system, that cleaning system, does not work properly, each one of us will be geared towards slightly different disease. So in essence, you can say, okay, so if we actually understand, if we can monitor changes that are related to the immune system passively in a dynamic way, can we actually discover that path that lead to from completely active working microglia in the brain to something that's starting to accumulate toxins, to something that is veering towards specialized type of toxin, and you can try to prevent that early on, or even more powerful, to push back along that path. That would be a very, very interesting hypothesis, way of thinking. One of the things that we know, for example, is that these microglia that work in the brain to eliminate the toxin, they are mostly active during slow waves, during sleep. So, and we do, like in our inflammatory diseases, such as like I told you, we are monitoring in Crohn's, we notice that people, when they are about to inflame also, just the week before that inflammation or at the boundary of the inflammation, they have more of the slow waves. So can we understand those immune changes, the changes in the immune system and its capability in a dynamic way if we are monitoring dynamically and try to stop diseases early on? I think I don't see why that is not a reasonable hypothesis to try to follow and investigate further. Yeah. Thank you, guys.